Now, some questions related to electromagnetic induction. As you can see, figure 10.1 shows a straight wire being placed, a wire AB which is placed in a magnetic field between the poles of a magnet, and A is connected to a galvanometer. So wire is moved vertically. It can move up, we can move it up, or we can move down. So state three factors that affects the size of deflection, like how we can change the amount of the current or the size of the deflection if we want to. Number one, what we can do, we can change the speed or move it faster or slower. If we move it faster, move the wire faster, there will be a greater change in the magnetic field. As a result, there will be greater induced EMF. Or what we can do, we can use stronger magnet. That is the second thing. Or what else we can use? We can use more turns or increase the number of the turns. So increase number of the turns of the coil which we use, that will also induce greater EMF. And how to find the direction, like if they say the wire is moved upward. If we are moving the wire upward, that's the motion of the wire. And the question is, state the direction of induced EMF. So how you'll work out the direction of induced EMF? Your first finger, use the right hand rule, and your index finger or the first finger will represent the direction of magnetic south, the south pole of a magnetic field. Your second finger should point in the direction of the current, but we don't know the current that we are finding, so we cannot point. The second finger automatically shows us the current, direction of the current, and the thumb will represent the motion of the wire, the movement or the motion of the wire. So motion is upward. I will apply my right hand rule. First finger, the index finger should point towards the south. My thumb should point upward. So what I will find, where the second finger is pointing, that is a current. So when you apply this rule, you will find your second finger is pointing into, so the current is in this manner. So this is how the current is moving in the wire. Is it clear that how we work out the direction of the current by using the right hand rule, Fleming's right hand rule? So in this question, figure 7.1 shows a horizontal conducting wire XY between the two opposite poles. So north and south poles are there, and there's a conducting wire X and Y, and that is connected to an ammeter. The first part is explained why the reading on the ammeter is 0 when the wire is not moving. So when the wire is not moving, there is no change in the magnetic. There is a magnetic field, but there is no change in the magnetic field. That's why there is no current. So when wire is stationary or wire is at rest or not moving, there is no change in the magnetic field. And when there is no change in the magnetic field, there will be there is no induce EMF, because EMF or current can only be induced when there is a change in magnetic field. And how there can be a change in magnetic field? Either moving the magnets or either moving the wire. Then the wire XY is moved, and there is a deflection on the ammeter that indicate there is a current from X to Y. So now there is a current from X to Y because the wire has moved. The question is, on the table, tick one box to indicate the direction of the movement of the wire and explain your answer. So first thing, we have to use the Fleming's right hand rule. According to Fleming's right hand rule, the first finger, the index finger, represented the magnetic field. The second finger represent the direction of the current, and thumb will represent the direction of induce. The thumb will represent the direction in which the wire is moving. So in this question, we know the current dimension, the current is from X to Y. We know the magnetic field, but we don't know the movement of the wire. So we have to find where the thumb is pointing. That will be the movement of the wire. So your index finger, the first finger should point towards the magnetic field. Whenever we are finding the current or relation between current, motion, and the magnetic field, we will use right hand rule, because whenever there's a change in magnetic field, there's induced EMF. So in that case, we will use a right hand rule, in which the index finger, the first finger, it will represent direction of magnetic field and magnetic south here. The second finger point in the direction of current, and the thumb automatically now will show the direction of the motion. So when we apply the rule here, we have to find which direction the thumb will be there. So the current is from X to Y. This is how the current is moving. So we will use the right hand. The index finger, the first finger should point towards the south. So first finger or index finger of a right hand point towards the south or towards the right hand side. Your second finger should point in the direction of the current, you can see the current is pointing into the page. So your second finger point into, your index finger should point. So this is the first finger, the index finger, which is pointing in the direction of magnetic field. Your second finger will point in the direction of the current where thumb is pointing. When I apply the rule, my index finger is pointing towards the right, current is pointing into. So where thumb is pointing, thumb automatically it is pointing up. So it means what is the motion of this wire or the movement of the wire? This wire is actually moving up. So we have to take, the options are given. We have to take an option. Which one? Explain the motion of this wire in a magnetic field. So which direction this wire is moving? It is moving to the top of the page, like it's going up. So that's why we say it is moving towards the top of the page. Then explanation. Explanation means why there is an induced current or why there is an induced EMF. So when we move the wire upward, there's a change in the magnetic field, and why the direction is upward for a motion? Because the magnetic field is from north to south or pointing towards the south. So the answer here, the wire is moving 90 degree or perpendicular to magnetic field, and the south is towards the right hand side. So the current induced from X to Y. So that is the explanation, because the wire is perpendicular and the south is toward the right hand side. So when we apply the right hand rule, we will find that the current is from X to Y. And in the question, the current is given we have to work out the direction of the motion. So sometime direction of the motion you have to identify for a wire, and sometime you have to identify the direction of the current. State what is observed on ammeter when x is moved in opposite direction. So if x is moved in opposite direction, if it was initially moving up, now we are moving it down. So what will happen? The deflection of the ammeter reading, or the needle of ammeter or deflection will be opposite. Deflection in opposite direction. So needle of the ammeter shows the deflection, but that deflection will not be in the same, it will be in opposite. And next one, if it is moving in the same direction but with a greater speed, so direction would change, but the ammeter reading, it will show a large deflection, because if it is moving faster, there will be a greater induced EMF, and when there's a greater induced EMF, the deflection will be larger. So if I move the magnet or the wire faster, then induced EMF will be greater. If I change the direction of the movement of magnet or the wire, the direction of the induced current will be reversed.